So this talk is part of a workshop that we're holding here at the Bolton Laboratories, which is about the future of humanity, the ecological being. And together we're exploring questions about what are the possibilities for us to, I guess, live different kinds of existence. And I think particularly with the notion of ecologies in mind. So this particular talk looks at how notions of ecological beings, I guess versions of humans that integrate their identity with the natural world, what kinds of forms of urban organization may be possible when we start to view ourselves in this particular way. So yesterday we heard a little bit about what an ecological being was, which is the person seeing themselves actually as being an ecology rather than a machine, so that an ecological being may regard the bacteria in their gut as being as much as part of their flesh as their muscles and tissues are now today, with our mentality that the human body is a kind of a mechanical object. And maybe an ecological being also starts to see green plants and trees as being part of their breathing systems as much as their lungs are, because they nourish the body with oxygen. So in that context then, with this idea that maybe a different metaphor, say, that carries our concept of what we are as creatures, then starts to have implications about the way we conduct ourselves in the world. And integral to that, I think part of our identity is our relationship, not just with the natural world, but with technology, the kind of apparatus that grounds us in an active engagement with the places that we live in and the way that we connect and communicate with each other. And in this particular talk, which is called Ecological Cities, I just want to make sure that ecological is actually understood with an I, because it represents instrumented ecologies. In other words, that even as ecological beings, we are still actively shaping, participating, curating, and editing our experience of the world almost continually. So the I in ecological stands for instrumented. It's not necessarily a mechanical technology. It's not necessarily any particular kind of thing that we do. It is simply that as creatures, we like to manipulate and, I guess, stack the odds, not just for our survival, but for our quality of existence in the world. So just so that we're grounded in this word ecology, which I might use a few times in the talk, just so that we understand what that means and that it's actually not just a misspelling on a slide. So within this talk, I'd like to particularly talk about how science, technology, architecture, and other creative disciplines may be entangled over the course of the century to potentially offer a new paradigm for human development. That sounds very grand, but I think right now that we are at a critical phase where we're thinking, are the strategies that we're using right now actually sustainable? Are these the ones that we're actually going to carry through with us into our 21st century, which is an age of megacities? These are vast metropolises that house more than 10 million people each, and they span for hundreds of kilometers. And of course, you know, this creates very specific problems, particularly like resource challenges, crime, homelessness, collection of waste. You know, the infrastructure needed to support these, you know, giant metropolises is already struggling, and we're only at the very beginning of the 21st century. So it raises some very important issues about ethics, about the structure of society, about how we create humane places in which we can inhabit. So I'm going to actually start with a dream. I'm going to start with an architect's dream. And the architect is, of course, Lars Spoibroek here, who speaks of a different way of imagining a reality. And he's particularly thinking of a way that we make things differently. So he says that he longs for the day when we can see objects forming like pools of mud, flowers on a wall, or clouds in the sky. as pure products in a context of pure productivity without any intermediaries. There would be no desires, no opinions, no critics, no designers, just pure flourishing. So he's stepping back from an engagement with reality, kind of re-empowering the, I guess, the technical systems around us as being very powerful actors and agents in shaping our experience of the world. In other words, there's an aspect in which the human, the anthropocentric aspects of being are starting to retract. So I'm interested in this, not because I particularly want to advocate it, but I'm interested in it because it sounds like a new form of nature. But Spoybrook actually imagines this kind of nature in cyberspace. But what if this kind of potency that he describes is not located in virtual reality, but could be achieved in the real world? And whilst our current design expectations of technology take place through these metaphors of production and effects of machine, particularly when it's framed within an industrial context, I'm going to start to talk in this particular lecture about a completely different kind of technology, a different operating system that shares the same language as the natural world and offers something that potentially could help us have a dialogue with the natural world. Something that Mike mentioned this morning. He was talking about his interest in our desire to mimic the natural world, and then how we connect with its real effects in that in that realm. And I want to be able to understand this as Isabel Stengers proposes, as an ecology of practices in which there is no hierarchy of truth, say by the sciences and engineering disciplines over, say, the arts and design specialties. Because I think that there is a platform through which a mutual exchange can take place, where we can re-inform each other about the desires and possibilities, and therefore kind of consensually shape a set of practices that maybe take us in a different direction to the way that we're heading right now. But right now, we urgently need an alternative to fossil fuel burning machines. Because although they have brought many benefits, we're now using them on such a scale and at such concentrations that they're damaging our environment and our natural systems that sustain us. And we're expecting a whole lot more of them, particularly in our cities, as our buildings are not only places where people live, but they also are the sites for the collective action of machines. You think about a skyscraper in New York and how many air conditioning units are heaving out the back and throwing out all the excess heat that they're driving out of those spaces. And according to the UN Population Division in 2012, another 3 billion people will need housing on this planet by the middle of this century. Currently, we have 7 billion people on the planet. Another 3 billion people are going to arrive on this planet, according to projections. And 2/3 of our global population will be living in our cities where existing infrastructures are already recognized as being inadequate in maintaining a basic quality of life through all these challenges that I mentioned earlier, like overcrowding and traffic regulation, for example. And actually these, although they sound very soluble right now, when they become so dense and so omnipresent, they start to threaten the lives of many people. So these concerns have emphasized that the future of our cities is also deeply entangled with the survival of our species. So modern humans have proliferated with the rise of cities, but more is not necessarily better. Indeed, many complex questions arise from the needs of metropolitan citizens in this age of megacities, where it is simply not enough to build, but to build well for our communities. And in contemporary terms, we might describe this desire as one for sustainable living, a term that's been inspired from the 1987 Brundtland Report on Sustainable Development, which sought to meet the needs of current generations without compromising those of future ones. But if that is indeed the aim, then we've already failed on so many counts. as the global paradigms that underpin modern human development are relentlessly reducing the quality and quantity of natural resources. And they do not even begin to address even more insidious processes that will impact quite dramatically on global populations over the next few decades, such as water shortages, air quality, and desertification. At almost every environmental summit, there is an impassioned plea for a radical shift in our global practices, away from the intoxicating efficiency of industrialization. And of course, it's made us wealthier, more efficient, more populous. But on the downside, it's accelerating this progression towards a potential environmental catastrophe. But in response, governments and industry have adopted the concept of sustainability as their own, to represent the kinds of practices that seek a better relationship between human development and the environment. In fact, sustainability has become the buzzword of our time and has been reinvented for almost every purpose that it's been applied to, from building sites to environmental sensitivity, food packaging, health and economic growth. In fact, there's very little in contemporary society right now that is not positioned as being sustainable in some way or another. Yet whilst we're being more mindful about the way that we consume and build, we've not actually changed the underlying paradigms of resource consumption and scarcity economics that underpin the modern lifestyle. Consequently, we've only made incremental changes to the actual processes that, that shape our world since the beginning of the environmental movement in the 1970s. Yet, owing to our economic concerns, political directives and funding incentives, we continue to protect our increasing use of machines and are even redefining sustainable criteria according to industrial agendas. For example, we're regulating building performances according to the needs and characteristics of machines. So standards such as LEED and BIM are mostly focused on energy availability, which Jeremy Rifkin, who is the author of The Third Industrial Revolution, observes are central to 21st century economies. Yet as innovative as these practices may be, they are, even in terms of their distribution, they're not different ways of working. Indeed, they can only be regarded as better environmental solutions because they're less damaging for ecological systems, not because they actually promote vital biospherical relationships. In other words, the environmental currency of modern buildings and their methods of production is in their relationship to industrial efficiency, not biological energy. Yet it is biological energy that enriches environments and enables industries to thrive. In the 1939 trailer for the World's Fair, there was actually this incredible moment where the film attributes industrial success to the productivity of soils. And I was just thinking, is this something that would be mentioned in a World's Fair trailer today? And I think the answer actually is no. Somehow or other, over the course of the 20th century, we've lost that connection with earth and soil, and we've made it somehow or other separate and distant from our everyday experiences. But what if it was possible to redefine sustainability, not as a resource-reducing tactic, but as a life-promoting approach to the built environment? So to change the impacts of technology on our natural systems, we must first tackle the challenges that architects, environmental scientists, and engineers all face by addressing the deep association between our ecological systems and the evolving concept that we call nature, which is framed by passionately held belief systems. And we need to do this so that we actually understand what we're trying to change. So whilst we may all think we have a clear understanding of what nature is, our ideas are actually rather complexly shaped by sets of ideas about ecology, culture, and technology. In fact, it's actually impossible to have a conversation on the environment without invoking our preconceptions about the natural world, which relate to our ideas about humans and non-humans and the behavior of our material realm. So to more clearly see our environment, commentators such as Timothy Morton and Slavoj Žižek first ask us to deconstruct the image of nature before we can really engage with scientific concepts such as ecology and to make proposals about what new sustainable solutions could be. But to do this, we must first understand the context of architectural construction using informed propositions that are free from unconscious postmodern aestheticisms which influence our expectations of the natural world. In other words, when we're building sustainable architectures, we're putting little green hats on buildings or little furry vertical walls because somehow or other they remind us of a bucolic vista that we might see in a pretty landscape. And this is what Zizek and Morton are asking us to abandon and actually start to really observe what is around us. And when we take off our green-tinted lenses, we discover an image of nature that is strange and unique to our times. In contrast to the nature recognized by modernism, a passive, romanticized, domesticated resource that is simply awaiting consumption by machines, 21st century nature is empowered, lively, and possesses a technological character. And how we work with these unique qualities will define the success of our 21st century relationships, and also our success of environmental practices, as these frameworks will help us establish the new opportunities that may help us move towards much needed new production platforms that could underpin our human development. So industrial processes to environmental design and engineering speak of a modern image of nature and seek solutions through form finding or mimicking biological functions, such as in the practice of biomimicry, which do not deal with the inevitable time-based change within natural systems or even its unique, lively materiality that's capable of many acts of transformation. In contrast, 21st century nature's innate technological characteristics lend themselves directly to producing new kinds of environments where sustainable buildings may be characterized as being a designed expression of nature and therefore a part of it, because and so that it would be seen as being good for an environment because the two things are seamlessly connected. So 21st century nature, therefore, requires us to take a process-oriented scientific paradigm to help design and engineer with its technologies, which are at far from equilibrium. So the technological character of nature is not like machines, kind of ontologically springing from an equilibrium state. In other words, they possess lots of energy and they can do things. And they form rich material connections that issue the processes and substances of life. Now, these processes are currently being technologically explored in research fields of artificial life and synthetic biology, where biotechnological advances have enabled us to directly manipulate living things and have offered a variety of platforms for designing and engineering directly with lifelike processes. Yet, if we're going to produce technologies that operate differently than machines, we need a new way of imagining how they work and the terms that we use to shape our expectations of them. Otherwise, we will find ourselves just slipping back into the language and expectations and images that we associate with the industrial age, because that is the framing of our world right now. So such a vocabulary can be found if you dig deep into process philosophy. And it's existed since the time of Heraclitus, which is this gentleman here. And over the course of the century, so he was an ancient Greek philosopher, various philosophers have actually started to explore the idea of a world in continual flux, rather than one that can be rationalized and analyzed by understanding its parts. And I'm particularly interested in the work of Gilles Deleuze and Félix Guattari, who have described such operating systems, these aspects of reality that are in flux, as being performed by assemblage, something that we heard a little bit earlier about. So these are formed by spontaneously created, loose, reversible associations between heterogeneous groupings of agents, and give rise to things that with lifelike properties, such as soils, which are a giant body that inhabit specific regions of the earth. I mean, soils are really interesting because they're not, strictly speaking, alive according to our scientific criteria. And yet they have a lifespan. Soils will get old and they will die. Soils have, multiple systems to nourish themselves. We can stress them out. We can age them. And these are all the kinds of qualities that this alternative operating system the assemblage actually possesses. Now, to date, these ideas have really existed in philosophical theory, and they have not been materialized and tested experimentally. And yet developing this concept of assemblage into a functional operating system could really offer us some new kinds of ecological technologies that may shape our ideas about sustainability, that are not constrained by industrial frameworks, that can be described by different linguistic and semiotic sets of ciphers, and may potentially then enable us to generate new kinds of design and architectural encounters. So to interrogate how the assemblage may actually be applied and tested as a technological platform, I identified a model called the Bootery System, which was first described in 1892 by Swiss zoologist Otto Büchli. Now, he added potash, which is an alkali, to a field of olive oil, which is mainly oleic acid, but not entirely. And this is a reconstruction of that original experiment, except we didn't use potash, we used sodium hydroxide, 3 molar. And also we put in a water-soluble blue dye so that you can actually see what happens. And this looks like one of those clean clothes adverts. You know, here's the packet of super duper product, and now we're going to put that on your clothes. Oh my God, your greasy clothes are just dissolving away all that dirt. Look at it go. But what's happening in this is really, really interesting. So although this initial experiment was described 100 years ago, the intention for Büchli was actually to see whether or not chemical systems had lifelike qualities. So this was a kind of test for vitalist theories. So he was saying, well, actually, if I can transform a drop into something that reminds me maybe of a protist, a single-celled organism, then really am I starting to get close to a strategy of producing life in the laboratory? And Büchli was really quite excited by this particular experiment, because as you can see, there's, you know, the movement is outwards, a bit like one of those amoebas. I don't know if you've seen them, those blobby unicellular creatures that you can just see in a drop of water using a high-powered microscope. And so you can see all this movement going on, but really, because he described it in 1892, and because the basic chemical reaction that's driving this is simply the production of soap, it really wasn't considered to be all that interesting for the scientific community. And it lounged around as a set of drawings in old, I think old German textbooks. And really not much happened to it until I came along with a modern microscope and started to look at it underneath a small magnification ×4. And as you can see, that was all done at scale, so you can actually see this happening with the naked eye. But actually, when you look underneath the microscope, you start to see some very interesting things happen. So the first thing that I was struck by was that this form of self-organization was a spatial process. This was happening, this soap-making reaction was happening across time and space. So when you inserted time and space into an equation, you started to get these incredible kinds of relationships. So you can see that this is an interface between oil and an oil droplet and a body of sodium hydroxide that's managed to seal itself off in quite a large amount of product here. And all of these agents act very differently. You can see there's this interdigitation or osculating movement that they do, a kind of a kissing action, where the droplets look like they should be fusing, but they don't. There's like a chemical, it's meant to be wildly anthropomorphized. There's a kind of chemical dialogue going on here. They're negotiating boundaries. They're forming bodies. The bodies are heterogeneous. They're not all the same thing. But there's an awful lot of self-organization going on in this process. And some of these droplets only last for several seconds. But actually, a proportion of them, let's say around about 10 to 15% of them, are actually having this prolonged lifespan, let's call it. I'm using terminology that's wildly anthropomorphized, but I'm just trying to convey the kinds of sequence of events that we're starting to describe. Now, this is a slightly higher magnification. This is at ×10, so it's really, really hard to capture something in focus all the time at ×10 when it's jiggling about. But we have two droplets here that have survived the first process of natural selection, where the very vigorous chemical reactions literally burn themselves out and form little soap sculptures. Now, these haven't produced such large amounts of product, so it means that their interfaces are still free to keep on interacting with the environment and also, very oddly, with each other. Now, this started to be really surprising for me because these droplets actually were exhibiting extremely lifelike qualities. They could move around their environment, they can interact with it, they can interact with each other. They start to make sculptures and products, and you can just about see a little black dot that comes in and out of focus in both of those droplets. And that actually is the site in which almost like a tail of soap occurs. And these soaps are like microstructures. You can see them with the naked eye. You could start to see them on that first slide or the first video that I showed there. And what's even more interesting is that the soap structure is always produced at the posterior end of the droplet, and the movement is always on an anterior end. Now, this is very interesting because it means that the spontaneous organization of the molecules in this system have an anterior and posterior without any external information on the system. And it really is produced just by the physics and chemistry of the system. There's no magic ingredient. This is, the product of what we would call self-organization. And although we understand there are physical and chemical factors that involve feedback systems, some positive feedback systems reinforcing each other, some negative feedback systems that are quenching each other out, we still actually don't really understand every single mechanism or kind of exchange that's going on. But we can actually stand back and go, oh my goodness, this is something that looks kind of lifelike. You see that first little bit of product starting to form here, and another there on the other side, on its posterior side. So we're looking at its posterior. So we can actually start to look at this and think, well, this is very interesting. It gives us a snapshot of possibilities, of dynamic chemistries that possess some of these remarkable qualities that we may attribute to lifelike processes. And immediately, by looking at these, we can start to imagine if we could instrumentalize these, if we could find a way of operating. You can see the little, look how it goes through these incredible little jumps. So they seem to remain in a particular state for quite a while. Then they'll go through a little jump. Now this one here, which now starts looking like an ice cream cone, that the cone starts to extend quite rapidly until it becomes to another transition point, which I call the werewolf point. Okay, and at the werewolf point, there seems to be a relationship between the consumption of the droplet's surroundings and the weight of the product that it's making that causes this systemic agitation. So the droplet starts to shake around. It's and it goes very, very fast, and then it becomes really hairy, and then it kind of stops. So it's almost like this pre-terminal agitation that droplet undergoes. So that these very characteristic phases that you can actually see in what should be just a soap-making process that was so unremarkable that nobody bothered looking at it for 100 years with a microscope. So I was kind of intrigued by this. Because I was wondering, well, okay, so these might be interesting, but bacteria do it a lot better because they can survive a lot longer. I mean, these systems will go on for 40, 50 minutes. Often, just when you want to go and get something that will allow you to do some kind of test, they stop and become very inert and really cheese you off. But this is my favorite movie of all time. This is two populations of these Bootery droplets. So they're in a field of olive oil here, making microstructures. And very interestingly, they do have this population scale interaction with each other. So the away team has just come to check out the home team, which is doing all this building. And what's really interesting here is that the system undergoes some unexpected transitions. All of a sudden, we get this reorganization of activity and morphology within the system, whereby the droplets suddenly move away from each other, and they suddenly change the nature of their product-making process. So they change in both terms of their morphology and their behavior. Now remember, these are just simple drops of alkali and oil with a few probably flavor and you know, kind of different impurities in it. But that's an extraordinary transition from something that doesn't have a central program. So it starts asking us questions about, you know, well, when we think of the way that we describe life and the way that we're trying to understand how maybe life and living systems actually work and come about, are we using the right framing for these experiments that we're setting up? I mean, are there other ways of looking at these systems? And I think one of the surprising things about these assemblages is that although it can undergo this transition phase, or something that you know, maybe might be called a punctuated equilibrium, this sudden leap in its development, they're actually really rather predictable. Okay, and again, yesterday I said, you know, these assemblages are a bit like thinking about how you make a cake. It's not that anything goes, but you know that if you put your eggs and your sugar and your flour and your butter into your bowl and you mix it all up, that when you know, you or your grandmother, you know, puts it in the oven and takes it out, it's going to range from something from the dirty black biscuit to the fantastic gâteau. And so that system never becomes something else. It is always cake, but a cake with particular sets of characteristics. So when designing and engineering with these kinds of systems, we're already aware of these kinds of practices that we might be able to use on systems that have probabilistic rather than deterministic outputs. And we might describe those practices as cooking and gardening and agriculture, or bringing up small children, or herding sheep. You know, that there are things that you can generally achieve, you know, when you apply yourself to these systems. But hell, are you totally in control? Not really. But that's actually not a problem. What it means is that these kinds of systems have particular kinds of applications when we're thinking about how we might work with them or use them in the world, when we actually think about them as being a kind of technology. And again, you know, when they reach these transition points, when we've already heard of the term tipping points in ecosystems, you know, which are these irreversible states in which these thresholds are reached, and beyond which there is, you know, no point of coming back. So essentially, you know, we still don't really understand how we might take something towards a tipping point, or how we might prevent one from reaching one. But these are questions when we can actually start to see these operating systems that we can start to engage in. So for the basic operating system for this assemblage to be useful, we need to understand how we might engage with its operations. So in this particular case, we can, and I think for assemblage in the whole, we can actually work by changing the internal state of the droplet, so we can add chemistry, which is essentially what you do with a machine. You change the internal state of the machine by adding a cog or extra energy, and then the machine works from the inside to enact its program. But uniquely with the assemblage, you can also change the external conditions to alter the influence of the system. And so we're starting to think now that we've got a portfolio of possible forms of intervention, which could be understood in a new field of natural computing. And it's a term that was coined following Alan Turing's interest in the computational powers of nature. And so using this field of natural computing, we can start to firstly think about how we may compare and contrast a natural computer, or assemblage, with a mechanical system. And this is just really a little thumbnail sketch just to show us how we might start to think about our operations differently. So the component of a machine is an object. That's right, an object is without any agency. In an assemblage, as you can see, those droplets are empowered. They're already doing their things. I don't have to instruct them. They're using chemical energy that is derived from the reaction itself to actually compel and propel themselves through a medium. In terms of the orders in machines, they're effectively in series and hierarchies. But in this assemblage, it's an incredibly parallel, non-hierarchical system. The energy from machines always comes from outside. And with the assemblage, actually both intrinsic and extrinsic forms of energy. So you can provide energy to the system, which may prolong its interactions, but it also generates energy from within. And we can harness both of those strategies to try to prolong some of these interactions. In terms of control, in machinic systems, we have hard controls. In other words, we have to very clearly define what the machine is going to do. In an assemblage, we really need to work with forms of soft control. We need to incorporate the agency of the system in the strategy. And so necessarily it has to be a soft control system because we're dealing with a probabilistic system, not a deterministic one. And in terms of transformation, the assemblage, I think, characterized itself as a discrete form of technology. So Gilbert Simondon described two forms of technology. One, which was the machine, which he said has a totalizing paradigm. The second one was a cybernetic system, which dealt with adaptation, feedback loops, that allowed a system to acclimatize itself to its surroundings. But I would say that the natural computer represents a third category of technical system, which allows for transformation, I mean complete transformation in the system, particularly when those tipping points are reached. So when those droplets reacted together and suddenly did something else that was quite unexpected, that is a form of transformation that this technical system possesses that I think is unique, and I think it creates the condition for a new technological category. And so, I mean, this becomes interesting, okay? But in order for us to think of this as being a kind of technology, we have to be able to use it as the human scale. We actually have to be able to understand how we might access these properties. Now, I'm just using these as models. I'm not saying that I've solved anything. Really, what I'm doing is using this Bootery system as a lens on possibility. I'm not proposing this as being any kind of final solution. But what is interesting about it is that we're actually dealing with a computational system. So if we're looking at a natural computer that is inherently parallel. It is made up of atoms, molecules, complex chemical assemblage that couple information flow and energy transfer with matter during the computational process. We don't need a 3D printer because this stuff will make its own forms of solutions, let's call it, or forms of expression. It does not use top-down programming, such as genetic codes, but orchestrates the intrinsic power of matter as a creative agency and opens up new design and engineering possibilities. So in order to start to instruct these, I am by no means an accomplished chemist, but I used very simple chemical interactions just to start to demonstrate what I meant by some of these principles. So let's call this as a form of applied design philosophy. So what I did was I added some iron salts which interact with the sodium hydroxide, the alkali body here, and it produces forms of iron hydroxide here, which are the dark brown structures. And actually they then become magnetite, a form of iron oxide, which can actually, if you use a strong earth magnet, you can actually jiggle them around inside the droplet. So these are really like forms of really simple chemical gardens. I'm not proposing that this is sophisticated at all. This is a prototype, a demonstrator, proof of concept, as it were, a sketch. And I guess that is really what we're striving for today in the workshop. Another thing that I did was, okay, so we can think about how we might change internal systems to alter the behavior of these systems. Well, what about if we change external systems? And when I added alcohol to the olive oil, what I found was that the Bootery droplets loved it. They would stampede towards it and hug each other in groups. They would become extremely vigorous during the hugging period, and then they would suddenly become incredibly inert. So I think this has something to do with changes in surface tension of the droplets. Again, because this is complex, it's really hard to actually verify that. I'm sure we will do it at some stage, but essentially the working hypothesis is that these rapid interactions are to do with kind of population scale changes in surface tension, and then a kind of final chemical process in which the alcohol and the soap create a very rapid precipitate, which prevents further interactions. So really the lifespan, let's call it, again, anthropomorphizing, the lifespan of these actually depends on these interfaces being open. So if I start clogging them with products, say like around here, you can just start to see the product forming. That bit of the droplet won't be active. And so gradually these surfaces clog up, and that's when the system becomes inert. Not only that, if you try to scrape this stuff off, and I have tried, once the system has become inert, you can't invigorate it again. So once it dies, it can't be resurrected. There's a systemic change that happens within the droplet. Again, something that I really need to do more standardized experiments on, but it was an initial observation that I found quite interesting, that the end of the dynamic phase of these droplets seem to be associated with this, an almost an irreversible shift in the system. So the other things that we could do is to scale up the system so that it can, so now that it's no longer a millimeter in diameter, which was the size of the droplets that were produced in that initial video I showed, but actually this one here is probably about 3 centimeters in diameter. And you can see it's looking kind of murky. And that is because in order for me to get this droplet up to 3 centimeters in diameter, I had to take a product from the reaction and reintroduce it into the system. So I'm introducing an inhibitor into the system, which actually slows everything down, but allows the body of these droplets to grow. And it gives a different dynamics to the system. So instead of moving around vigorously, they actually start to grow a bit more like chemical stalactites. And so you start to get heavy precipitates kind of extruding themselves out of the bodies of these larger droplets, and then reprecipitating them on the bottom of the container here. So we can scale them up. We can scale them up by increasing the sizes of the bodies. But also we can scale them up by entangling their operations with other systems. And here I worked with Philip Beasley, an architect, who designed this incredible cybernetic matrix called Hylozoic Ground. He was commissioned by the Canadian government to produce this installation in 2010. And he invited me to design a chemical system that would operate within this meshwork of interactions, which would sense the presence of people. It would squeak with artificial cricket sounds as two plastic surfaces kind of grated over each other. There was a lot of activity in the canopy, which was moving air through the system. And so what I did was I created almost like little mucus glands, little sensors here, that could detect carbon dioxide very notionally, very poetically in the environment of the installation and gradually change color over the course of 3 months. So what part of the design specification of this was, it can't last 40 minutes, it's got to last 3 months. Whoa, how do we go about doing that? So I'm not saying that this is a technological system that really works efficiently or anything like that. This is a notional idea about the relationship between matter and transitions with time. It also poetically speaks of a giant smell or taste receptor. So if you think you've just crawled inside somebody's sinus here, all the hairy, frondy bits are hanging down, and here are some mucus glands that are literally showing you that they're tasting the carbon dioxide in the system. So again, kind of using design as a platform for experimenting with emerging technologies in ways that allow us to play and have different kinds of outputs rather than simple empirical results. So that in terms of a technological invention, this is probably a complete disaster. The amount of carbon dioxide that is realistically absorbed by that system is negligible. The aesthetic results, though, and the way that the system is configured are actually interesting, and they speak of new relationships between our being in the world and our experience of environments. So they have a different kind of value, particularly when we're thinking about emerging technologies and cultural appropriateness of these things. We think about the lessons that we had from genetic modification, whereby seemingly efficient technologies were pushed out into the world without a cultural context. Then this really created some tensions between what the public thought was happening with genetic modification and what the scientific and commercial communities were actually trying to achieve with these developments. So in some ways, these kinds of design-led platforms for speculative experiments on possibilities are creating a conversation that allows, again, this ecology of practices, sets of mutual exchanges to help reinform the context and also the possible applications or even developmental pathways of some of these really early kinds of discoveries, let's say, or observations. So essentially, again, when observing these systems then, I talked very briefly about the droplets and said, as a mechanical technology, whoa, they're woefully inefficient, and therefore we could call them a failure. But I'm framing that using the language of machines. How do I frame that with the expectations of an assemblage, which actually don't have these very clinical endpoints? In fact, I tried to create a map, a topological map, a map of relationships between various kinds of outputs of this Bootery system and wrapped it around what I saw here as a spiral of complexity and almost like ripples of time going outwards that were exponentially increasing. Again, this is not an empirical data set. These are curated forms that I derived over 300 experiments. And I used it in a way to examine the relationships between things rather than the separations of them, and used the notion of oceanic ontologies, which is a term that Matt Lee describes, which he says relates sets of ideas to maps rather than theories of concepts, and therefore can be shaped by the conditions of their environment. So any one particular drop, so really what it represents is we put a drop of substance, of sodium hydroxide, in the middle of this map here, and potentially, over the first few seconds, it has the greatest potential for transformation. But actually, there are other tipping points which may come from these almost like quantum events, chance events that are coming into the system that cause forms of transformation that are unexpected. Or there may be progressions in which we can actually see them becoming populations or more stringy structures or more individually productive kinds of systems or forming giant sculptures. So there are different kinds of trajectories that these systems or this particular system can undergo. But how we actually get them along these lines is still not entirely clear, but I can say if we increase the alkalinity of a system, we actually get a lot more soap products. So you can see just how so adding more soap-making stuff actually creates an awful lot of activity to produce those microstructures. So that there are clues in here, but it's not a complete map. This is a sketch of possibility, not trying to draw a tree of separations as in the tree of life, but actually trying to find communities of interactions, connections, so that maybe we can shift one set of potential outcomes into the direction of another one. So if we start to see the connectivity of things, we can actually start to see potential transformations within these systems, try to identify the windows of opportunity where these transformations can take place, and start to really experiment with the potential of a new technical platform. Those were essentially the design sketches that I was doing. And so again, in terms of scaling, in terms of making these real, I decided to take them outside into the living world and do an experiment in the city of Venice. And really what I did was came up with a formula for dynamic droplets that was based on the idea that, as I think Mike said this morning, Venice stands on these wood piles, and Venice is notionally sinking. It's a set of complex interactions, but it's standing on stiletto heels in mud. So if we could offload the point load of the city and put platform boots on the city of Venice, could we potentially attenuate some of that sinking and therefore address some of the problems that Venice may be currently facing? And we actually really used it as a site for a thought experiment and also for very simple laboratory experiments. So the idea was that we could create, and we did in parts create, a technology that would move away from the light. So it would move from the light-filled waterways under the darkened foundations of the city, where a second metabolism kicks in when the droplets are at rest. And it forms an accretion technology, which forms a kind of biocrete. And so essentially the girth of the foundations of the city grows a bit like, I guess if you got a load of Rice Krispies and put them together, a little pile of Rice Krispies, little empty shells accreting underneath the city. So they're not really very weighty, but they have this kind of sponge-like integrity. And what was interesting when I did a site analysis was that actually this process is already going on around every single waterside in Venice. So that accretion is happening by the collective action of microorganisms like bacteria, algae, shellfish. And so the idea was then maybe, instead of just being a technological solution, potentially these droplets could have a gardening-like relationship. Perhaps instead of thinking of pillars underneath Venice, perhaps we can think of an alternative kind of marine garden that performs some of the functions that we were thinking about when we came up with the idea, but maybe actually takes on a different kind of quality, creating new niches for marine organisms, so that we are co-constructing an architecture for Venice alongside the marine wildlife. And what was also interesting when we started to do experiments in tanks, we did one with Red Bull, and of course because it's a UNESCO World Heritage protected site, we can't actually do it in the water. So we actually carried aquariums all over Venice and put them on the waterway, invited the students from the University of Venice to join us, and we actually had little recipes where we could add droplets into the water. And you could see just how fast the droplets mineralized, how fast these little shells were produced, and how robust they were when we shook the tanks to mimic the waves. But whilst we were doing this process, we also observed that actually as the water levels went up and down with the shaking, that the droplets were very robust and could survive quite a lot of trauma. And we suspected that with time, or if we added silica to the system, we could probably get more stable structures once these configurations were more mature. But the idea was then, if the context of Venice changed, say the city dried out rather than drowned as the current predictions are, it gives a qualitatively different kind of technological output for this system. So as the waters recede, they start to coat the wood piles so that they seal the wood from the air, which is of course the thing that causes them to rot. So the pictures we saw this morning from Mike, which showed the giant liners moving through the canalways, what happens with them is they suck out the water from underneath the wood piles, and it exposes the wood piles to air. Another situation where it would be important is where people like Tiatini et al. Are looking at anthropogenic lift of Venice. In other words, when industry settled on the North Shore, it started to drink out the aquifers to drive its industrial processes, which contributed to the sinking. Now, so there are plans afoot to think about what would happen if we pumped water back into those aquifers and lifted the city by a foot over the course of 10 years. Now, if you did that, you would expose the city to the risk of loads and loads and loads of wood piles being exposed to the air. So again, this technology may actually be the kind of solution that we could think of as being something we could apply over the course of 10 years that was incredibly environmentally sensitive and could coat just those sections of the wood pile that needed coated, rather than trying to fill the entire base of Venice with concrete, which would probably contribute to the sinking of the city even further. So there were things about the potential that emerged and evolved over the course of the last 3 or 4 years that we've been asking some of these fundamental questions. We're not trying to reach a technological solution as a quick fix. We're really using this as a site for exploring what are the kinds of conditions in which these dynamic forms of natural computing could potentially exist in a broader context. So Venice is an ideal site to interrogate the potential of natural computers because it's got watery foundations. It's got a medium in which things can move around. Resources can come in and waste products can be taken away. And so the other thing that was really important in this study was that infrastructure is absolutely key for the performance of these kinds of technologies, so that we potentially could get these relationships that are life-promoting, not just for humans, but also for entire local ecologies. So we need to think about infrastructures. Now, before I do that, I just wanted to respond to the talk this morning about Kate Maguire's feather sculptures, because one of the assemblages that I started to notice as I was spending time in Venice, terrible place to do field research, don't try it. One of the things I was noticing that I was finding pigeon wings, just random pigeon wings. And I started to get kind of interested by this. I was walking along to the laboratory, ECLT, European Centre for Living Technology, and I'd go across St. Mark's Square, or I'd go across an alleyway, and I'd find just pairs of wings. It looked like there'd been a predator, but quite what those predators were, I wasn't entirely sure. It was also kind of ironic because at the time I first noticed it, there were a lot of posters around about advertising Thomas Mann's death in Venice. And so the mystery became, what is the cause of the missing pigeon? Is it some rampant cat in the city? Is it a very quick doggy? Is it a hungry homeless person? And one day, you kind of find the answers to these things in the most unexpected places. So for the squeamish, look away at the next photograph, because I actually caught the culprit red-handed. So the gulls have adjusted to life in Venice, thinking, you know what, fish are a bit tricky. Those little fat pigeons, lots of them around, nobody misses them. Let's gobble up the interior. And as you can see, for some reason or other, they don't eat the wings. They eat all the rest of it. And I just thought that was really interesting, particularly because of the feather sculptures that were used in his example of assemblage. And I was just thinking of these kinds of spontaneous assemblages that were being produced, not by people, but by herring gulls, and particular kinds of herring gulls. Not all the gulls would eat the pigeons. There were populations of gulls that had developed a taste for pigeons. And that was very interesting itself, something I didn't really go into in great detail. But to go back to infrastructure, I mean, infrastructure is incredibly important. So we saw this yesterday, the Henk Jonker's biocrete, whereby the presence of water in microfractures in the concrete activates extremophile bacteria that have been impregnated in its substance, which allows a protective coating of calcium carbonate to stop the fracture going further, or that's the theory. And the thing is that when we think about infrastructures, in our modern buildings, they're really poor in terms of supplying us elemental infrastructure design. Our kitchens and our bathrooms are designed as drains, not circulatory systems. Airflow is also equally unsophisticated in being directed through spaces like vents, rather than designed as breathing systems that optimize the potential for exchange. So the very conditions in which assemblage-based technologies could bloom are very limited within the modern home, because modern homes exist within mechanical infrastructures that are rich in electricity supplies and Wi-Fi systems. So with the appropriate elemental infrastructure, though, we may get new opportunities. So this is Philip's microbial home project, which looks at a different kind of infrastructure that is run by microorganisms that are feeding on domestic products such as kitchen waste to produce heat or compost themselves. And of course, there are loads of ranges of different microbes that will create experiences that with these kinds of infrastructural support could create different quality experiences in homes and cities. So this is an example of Anne Brodie and Simon Park's work with bioluminescent bacteria. I showed a picture of this yesterday, Philip Ross's furniture produced by fungal roots. And when we scale these up, we can start to think of, notionally again, Magnus Larsson's project Dune, which is a giant bacterial biofilm printer that is turning sand into sandstone and creating the fundament of settlements potentially within uninhabitable areas of desert. We're also using these kinds of systems within forms of agriculture. This is oyster texture. These are very special, unique assemblages of lifelike systems or living systems that are designed to filter out impurities and improve the drinkability of brackish or polluted estuary water. And these could be used, more in communities and homes and rivers. Again, another feature from the microbial home is to try to increase the number of pollinators within cities, using luxury items that are fueled by bioprocesses to try and increase biodiversity and keep our cities vibrant. But again, just continuing this notion of scale, I decided that I was going to go for gold and think of the most extreme scale that one could possibly imagine, going beyond the urban scale. So this is a sketch for Project Persephone, which is a real project and a thought experiment. It aims to construct the living interior of a world ship for the Icarus Interstellar Group's projects. And it's imagined as a giant natural computer within a starship. And then the idea is to really create the possibility of this within 100 years. So it's creating a new kind of set of design and engineering challenges. How do we design and engineer something that remains open and remains modifiable over a course of, say, 100 years? So we're thinking about how we go about designing something like that. But also it's asking questions about how do we create environments that support life. And again, it's challenging those questions about how do we design something that's good for the environment because it's part of it, as opposed to it is good for the environment because it is less damaging for it. So what we were playing with is the ideas of creating synthetic soils. How do we spatially arrange chemistry and kind of protobiologies so that it can create systems of exchange and spaces for catalysis that may give rise to lifelike events. So in other words, it's taking the design narrative and engineering narrative away from designing the object and designing the conditions in which an event takes place, which may be an object, it may be a living thing, it may be something else entirely. But essentially, it's looking at these infrastructures for design, thinking about environment as actually being a substrate for design interventions. And when we start to think in these terms, we can maybe even start to challenge some of the basic assumptions about the values within our existing cities. And so we can start to think about land as a multi-dimensional space, where we're no longer just dealing with two-dimensional geometric plots in which activity within these multi-dimensional spaces actually creates value through fertility. We can think of nature itself as being a technology, a transformer that can convert one set of substances into another, as in these algae bioreactors. We can think of a metabolic economy based on these exchanges, where we may even get urban scale metabolisms, where cities within particular sites with particular resources have certain kinds of productivity with very particular values and give rise to forms of meaningful employment. We can think of fertility itself as being a kind of currency that has value, which may be shaped by notions of exchange, metabolism, flow, robustness, and adaptability that increases the potency of a site and its livability, which create opportunities for different forms of microculture and microagriculture. So we can start to think of hyper-local processing and kind of exchanges that start to build communities. We need to start to think about non-human investors. Our living spaces are not exclusively human territory. Our vital ecological relationships depend on many, many processes that are performed by non-humans alone, which require different power relationships and different agreements, perhaps, between humans and non-humans within our city spaces. And these should remain open to negotiation so that systems may evolve. We may think of consumers now becoming producers. We all need to consume, but is there a way that potentially we can produce our own value and our own forms of exchange in a metabolic economy so that, whilst we could commodify intangible natural resources such as air, light, and soil, maybe we can constrain those within old power structures, but I think that maybe density exchanges and distribution networks could potentially go around some of these all-pervasive systems. This was another experiment that I showed yesterday, but for me this is a really important experiment talking about ethical exchange, so that potentially a metabolic form of economy has a particular kind of ethics and responsibility that is a mutual interaction between human and non-human communities. So here, of course, the title of the work is Victimless Leather by Symbiotica, speaking of the time when potentially we can have meat products without animal suffering. So within a society where we have access to alternative operating systems, perhaps we might even start to identify our roles within cities differently, maybe not as producers, consumers, or within particular class structures, but maybe describe our roles as being through the kinds of things that we do: architects, artists, scientists, designers, engineers. And perhaps this helps us re-articulate the conditions in which we exist. I think it is time to resist the doom, gloom, and skinny corporate corset that's wrapped around our urban communities by the industrial sustainability agenda. And we must allow ourselves to flourish again and crack a few austerity whalebones to make the transition from a culture that's paralyzed by reductive practices into productive ones that thrive on mutual exchange and generosity between humans and the natural world. And such collaborations are united by a common desire for survival and yet are characterized by their creative diversity of practices that increase environmental fertility and, when combined, may offer an alternative platform for human development, perhaps a bit like the one that Spoybrook described at the beginning, where humans are not receding but also are very, very present. And I believe this is a really important point now, because I think that design and science have a really exciting new relationship to forge at this time. Not in the kind of traditional sense of science as being the instructor through which certain paradigms must be understood and adopted, but as a way of accessing many different kinds of opportunities, not just for design and society, but also to increase the pertinence of scientific discovery and create the context in which science really genuinely can transform our ways of being. And I think that we would be able to discover an awful lot more opportunities for diversity. And I don't think that these are solutions to a restless world. I think that this simply increases our survival strategies and creates counterpoints for the current dominant narratives. I think that their main implications are really in our social and political and power structures. And I think that those are the very things that we really need to urgently address, rather than heading towards the technological fix, which seems to be the compulsion right now. So ultimately, I believe that we have a great future ahead of us. I think that we are at a unique time where multidisciplinarity is almost as necessary as the air that we breathe. And I think ultimately we will produce alternative forms of human development that will transform our existence into a truly deeply ecological future for all humanity and non-humanity that is in tune with the natural world. Thank you.